So because section 2.5 was relatively short, it was just a single video, and 2.6 will probably take a little bit longer, I figured we could also do section 2.6. We'll just do part 1 of this. I'll introduce rational functions, and we'll talk a little bit about determining the intercepts, vertical asymptote. We'll talk a little bit about the graphs as well. So to begin with, you'll notice that we are switching gears from polynomials a little bit here. We're now talking about rational functions. But the reason that this is included in this unit in chapter 2 is because, so let's take a look at the definition here. So a rational function is defined as any function in this format. F of x equals n of x over d of x. I'm using n and d for numerator and denominator here, where these two functions, n of x and d of x, are polynomials. So in other words, the way you can think of rational functions is rational functions are really just fractions of polynomials. I also want to mention that if d of x is just equal to 1, so that is a polynomial, d of x equals 1, then the rational functions just become regular polynomials. So all polynomials are actually rational functions. They're just kind of boring ones. Oops, okay. So let's get right into an example, and I'm going to show you the graph just so we kind of know what we're working with. So we're going to start off with the function f of x equals 1 over x. Now this is sort of considered the parent function of all rational functions. It doesn't quite work for all of them, but this is really going to be the most common one. This should be your go-to. When you picture a rational function, this is what you should picture. So let's go ahead and take a look at the graph of this function. So we're going to go y equals 1 divided by x. So you'll notice that if I zoom out here or zoom in, this graph kind of breaks in the middle at 0. And then it kind of does this weird thing, right? Because it goes two separate ways at 0. This is how most rational functions will look, and we'll see a couple more examples of this. A couple of key features I want to identify. So let me go ahead and head back to my notes here. So if you're ever asked to graph a rational function, it most often will look something like this. Notice that it never really comes into contact with the y-axis, and it never really comes in contact with the x-axis. These have a special name. These are called asymptotes, or you can think of them as sort of boundaries for the function. We'll be talking a lot more about asymptotes and what that vocab word means in this video and the next ones. Additionally, this graph, since it never touches the y or the x-axis, never touches either axis, this means there are actually no intercepts at all to worry about. Okay, and then the last thing we usually talk about when we introduce a new function is the domain and the range. So in this case, the domain is everything except for x equals 0. There's that boundary there. So I would say it's negative infinity to 0, open parentheses, and then union with 0 to infinity. For the range, looking at the graph again, looks to me like it doesn't ever cross the x-axis, which we've already talked about. So the range is going to be similar. The range is also all y values except for 0. Okay, so that's the first sort of go-to example. I want you to have this in mind. It's just sort of this image. whenever you graph a rational function, be thinking about this. We will change things as we go, but for the most part, this should be your go-to image. So now let's look at a different example where there's a little bit more going on, and we'll actually talk about how we might find intercepts and asymptotes if we were given this function. So let's take a look at this function. R for rational, let's go with 4x plus 1 in the numerator, and then 2x minus 3 in the denominator. And we'll be using this function for this problem. Now, one of the first things you should do, even before I give you an actual question to work on, is be thinking if you can't factor some stuff and cancel it out, keep in mind that there are a set of implied parentheses around the numerator and denominator, so you can't just pick x's and start crossing them out. You actually have to have matching linear factors, or quadratic factors, I guess, but you have to have matching factors in order to divide out by 1. In this case, there are no matching factors. There's nothing I can factor out of either the numerator or the denominator. They're in their lowest form. So the first step that I want to take here is I want to identify the intercepts. And let's go with the x-intercept first. Now, something I want you to keep in mind no matter what function you look at, it could be any of these, it could be a trig function, it could be exponential, it could be logarithmic, it could be anything. In order to find the x-intercept, you always set y equal to 0, because if you look at the graph, the x-intercepts have a y value of 0. So I'm just going to rewrite this function so that it's 4x plus 1 over 2x minus 3, and then all of that equals 0. Now, in order for a fraction to be 0, we really don't care about the denominator. So just as a quick reminder, 0 over anything equals 0, but anything over 0 is undefined. It's illegal to have nothing on the bottom. With this first part here, I just want to mention if a is 0, then it's undefined as well. This usually comes up in class. A question gets asked. If a is 0, well, then it's undefined. 0 over 0 is also undefined. So the point of this is we don't need to worry about, for now, this will come up later, 2x minus 3 equaling 0. So what I'm going to do is I'm just going to take that 2x minus 3 and I'm going to multiply it to the other side of the equation. As if it was just a number, I would just multiply it to the other side of the equation. Now 0 times 2x minus 3 is just 0, so now I'm left with 4x plus 1 equals 0, which hopefully looks pretty familiar. This is a linear single variable equation to solve. So subtracting 1 and dividing by 4, I should end up with negative 1/4. And remember, we were solving for our x-intercept. So my x-intercept is negative 1/4 and 0. All right, the next thing I want to do is solve for the y-intercept. Just like the x-intercept, no matter what function you come across, I want you to remember that in order to find the y-intercept, you set x equal to 0. So this means I'm taking my function here, 4x plus 1 over 2x minus 3, and I'm just replacing x with 0. So in the numerator, I just end up with 1. In the denominator, I end up with negative 3. So my y-intercept is the point 0, negative 1/3. Cool. We're just about done with this example. I want to finally find the equation of the vertical asymptote. So if we are thinking about our original function, which was, so here's another aside. So the very first function I started with, the 1 over x, our go-to. Remember that the vertical asymptote is this line right here, the y-axis. If we were to write that as an equation, it would be x equals 0. And this is essentially a point where the graph does not work. This is where we have some sort of issue. So this is where we have issues at x equals 0. And so what we're going to do with this function when we're finding the vertical asymptote, I want you to think about where does the function have issues. In other words, we're finding the domain. We're finding the x values that cause problems with the graph, which is really just the same thing as finding the domain. I say that because you have actually a lot of practice finding the domain for these sorts of functions. Remember before I said we're going to worry about the 2x minus 3 later? Well, now we're going to worry about the 2x minus 3. We can't divide by 0. I've already spent a lot of time talking about this in other videos as well as this one. We can't divide by 0. So when we're discussing domain, we're thinking about what can't we do. So let's go ahead and take 2x minus 3. We don't want this to equal 0. So solving for x, we get that x cannot be 3 over 2. And so we've actually just found the domain, but the question was asking for the vertical asymptote. So the vertical asymptote is that equation. Instead of as an inequality, we would just write x equals 3 over 2. So we'll go ahead and formalize this in just a moment, but I want to finish up the problem before we do that. I'm not going to do the horizontal asymptote, so I'll write this down, but this is for another day. There's a little bit more work to put into that. So we'll do this for our next set of notes. But at this point, we have basically a good idea of what this graph looks like. I know what its x-intercept is. I know what the y-intercept is. So these are both 1. The x-intercept is about there. Y-intercept is there. And then the asymptote is at right about there. So I already have a lot of information. I have the intercepts and I have the asymptote. In order to do a complete graph, we would really need the horizontal asymptote as well. So to finish with, let's go ahead and graph this function, just so we can check our work to see if we did it right. So I'm going to go ahead and do 4x plus 1. Notice I'm putting parentheses. If you don't put parentheses, Desmos won't like you. And then 2x minus 3. So here's my graph. If I do x equals 3 over 2, we got the vertical asymptote right. And then let's go ahead and check our intercepts, negative 1/3 and negative 0.25. I just realized I put them as positive values instead of negative values. So let me go ahead and fix that. Oops. So they really should have been about there. So then our graph maybe looks something like this. But again, without the horizontal asymptote, it's kind of hard to get a good picture of this graph. All right, so just to go back to the vertical asymptote, I hopefully gave you some intuition when we were doing this problem as to how you might solve that. But if you would prefer to have a more formalized version of this, just know that the equation for the vertical asymptotes, there could be more than one. Again, on video notes for another time. of a rational function that looks like this are given by the solutions. So it's sort of the opposite of domain. We're now looking for the solutions of the equation, whatever the denominator is, set it equal to 0 and solve for x. So you set d of x equal to 0 and then solve for x. And that's it. So that covers our talk for today. Section 2.6 part 1, we're really just looking at intercepts and also vertical asymptotes. In the next set of notes, we'll take a deeper dive into rational functions, and we'll start taking a look at different types and making things a little bit more complicated.